Hello, everyone. My name is Scott Melville, and I am a Stephen Hawking Fellow at the University of Cambridge in the United Kingdom. I work on various aspects of effective field theory in both cosmology and particle physics. And today, the organizers of Cosmology from Home have very kindly invited me to review some of the recent progress in developing positivity bounds for cosmological effective field theories. In a nutshell, positivity bounds are a way of connecting physics on very different scales, particularly how certain properties of the fundamental physics on very small length scales can have measurable impacts on the observations that we make on very large length scales. Now, this is particularly important as we enter the age of precision cosmology, with new data and new windows into the large-scale universe becoming available. We must be ready with the complementary theoretical tools to extract as much information as possible about new fundamental physics. So my plan for the next 45 minutes is to answer three main questions. First, I'll explain in more detail what these positivity bounds are, why they're so important, and sketch at least an outline of their derivation. Second, I'll discuss how these bounds can be implemented in cosmology, in particular describing two recent strategies that we have developed and their consequences for effective theories of dark energy and inflation. And finally, towards the end, I'm going to look towards the future, outlining my vision for this positivity program and describing the next steps which will take us beyond what is currently possible. Let's get started. So let me begin with a big picture overview of what positivity bounds are designed to achieve. The idea is that often the fundamental high energy physics that we are trying to uncover cannot be accessed directly given our limited experimental reach. Positivity bounds are relations between the UV and the IR, which can be used to bridge this gap, connecting our low energy observations to properties of the underlying UV physics, and vice versa, using UV consistency to guide our IR model building. They are formulated in the language of effective field theory, which is the principle that at sufficiently low energies, only the lightest degrees of freedom can be excited. So a low energy observer can describe their system using a simple phenomenological Lagrangian, in which all of the heavy fields have been integrated out or averaged over. The goal behind positivity is to infer from this low energy EFT properties of its underlying UV completion. We do this by considering the following observable: the scattering amplitude for two light particles to come in, scatter off each other, and go out again. In the UV, this scattering is mediated by all of the detailed UV physics. But in the IR, all that UV information gets packaged up into a series of constant couplings, which in practice is what we measure. The cartoon is that each UV theory gets mapped onto a particular set of EFT couplings. And so one way to search for new physics is to guess at particular UV theories, solve for and integrate out all the heavy fields, and see if the resulting EFT coefficients that you land on match experiment. But this can be a very inefficient way of searching for new physics. And in cases where you have limited experimental data, like in cosmology, this simply leads to a long list of very specific UV models, which are all broadly consistent with the current data. So another approach that you might take is to remain completely agnostic about the UV, treat it as an unknown to be determined, and focus entirely on measuring the EFT coefficients in the IR. The problem there is that you have no real guidance of where to look. Any region of parameter space seems as good as any other. And so now your task is to fix what can be quite a large number of completely free parameters. So positivity is a third hybrid approach to effective field theories where you focus on UV completions which obey certain consistency conditions like Lorentz invariance, locality, causality, and unitarity. This subset of healthy UV theories maps onto a particular subset of EFT coefficients. It's now no longer the case that any EFT parameter is equally good. Only some values can be UV completed, can be consistent with these basic properties at high energies. So this is a very powerful way of approaching our phenomenological models, because even before you have any experimental data, you are able to use UV consistency to place some constraints on your EFT couplings, telling you which regions of parameter space to explore. And then, if you are able to measure some of these coefficients, you now have a way of converting those measurements into a concrete statement about the UV. Because if your measurement lies outside of this positivity island, then the underlying small-scale physics must be violating one of these assumptions. You've learned something very profound. So my goal for the rest of the talk is to show you how these UV properties lead to positivity bounds in the IR, and how these bounds can impact the field theories that we use in cosmology to describe dark energy and inflation. Now I want to tell you how these fundamental properties of Lorentz invariance, locality, causality, and unitarity are encoded in the scattering amplitude and can be combined to give positivity bounds. So first we have the space-time symmetries, and really these are fixing the kinematics of our problem. For instance, for a single particle propagating through space-time with momentum p, Lorentz invariance says that the corresponding amplitude can depend only on the invariant p squared. Next, locality and causality, when combined, they give an integral representation of the amplitude called a dispersion relation, which connects the IR and the UV. For instance, for an interacting propagator, we can express it as an integral over free Feynman propagators weighted by the imaginary part of the amplitude. Now this is related to causality because these free Feynman propagators, when written in position space, are really just step functions, which are 1 inside a future pointing light cone and 0 everywhere else. So this representation of the amplitude is really a causal representation, the amplitude in terms of an integral over momenta that point inside the future light cone only. So this is the bridge that we'll use between the IR and the UV, because we can evaluate the left-hand side at very small p squared, at very low energies, and causality guarantees that it's equal to this integral over very large p tilde squared, very high energies. Now the final ingredient is unitarity, which guarantees that this integrand is positive. Now loosely speaking, unitarity is the condition that all probabilities have to add up to 1, and this places restrictions on the real and imaginary parts of these amplitudes, known as the optical theorem. This is best visualized diagrammatically. So on the right-hand side here, we have a sum over all n particle states that could mediate this interaction. So the sum is over the amplitude that my one ingoing particle splits into n intermediate guys, times the amplitude that the n intermediate guys recombine into my final one particle state. Now, crucially, we may not know what all of these different amplitudes are, particularly in the UV. But unitarity guarantees that they only appear in these positive combinations of A times A star. So now we can put all of these ingredients together, and we can show that if you Taylor expand the amplitude at small p squared, the coefficients in this Taylor series can be expressed as integrals using causality of things which are positive by unitarity. So this is how Lorentz invariance, locality, causality, and unitarity come together to give constraints on the coefficients in your low energy EFT. Now, this simple amplitude for a single particle propagating, it's convenient for showing how these different ingredients fit together, but in practice, these positivity bounds are less interesting than the analogous bounds that we can place on the interacting two-particle amplitude. This is the amplitude for two particles to come in and scatter off each other. But the concepts are exactly the same. So I'm going to go through each of these boxes again for the two-particle scattering amplitude quite quickly, and then move on to a discussion of how these analogous positivity bounds can be applied in cosmology. So the space-time symmetries, again, just fix the kinematics of our problem. Now there are four different particle momenta, but there are only two independent Lorentz invariant combinations, these Mandelstam S and T variables. Now physically, S is the center of mass energy, and T is related to the angle through which the particles scatter. Causality and locality, again, give a dispersion relation which relates the amplitude at low s in the IR to an integral of the imaginary part of the amplitude at very high s in the UV. The qualitative difference is that now there are two contributions on the right-hand side, which reflects the fact that there are now two different ways that this process can take place causally. Either it's particles 1 and 2 that are coming inside the light cone and producing particles 3 and 4 going out, or it's particles 1 and 4 that come in and interact to produce particles 2 and 3 going out. The other, maybe somewhat technical difference is that these integrals on the right-hand side, often they don't converge because the imaginary part of the amplitude can grow at large s. There's a simple way to fix this. Rather than consider the amplitude itself, we can consider s derivatives of the amplitude, which increases the power of s in this denominator here. And locality ensures that as long as we take two s derivatives, then these integrals will converge. So the final ingredient is then unitarity, which again fixes the imaginary part of the amplitude as a sum over the possible n particle intermediate states that can mediate this interaction. And in the forward limit, where the incoming momenta are the same as the outgoing momenta, we see that again, this is a strictly positive combination of amplitudes. So now we can put these ingredients together and bound every Taylor series coefficient in this low energy expansion of the EFT amplitude. So the simplest bound is the coefficient of the s squared term. And the fact that this guy has to be positive is really just the straightforward analog of the one particle positivity we saw a moment ago. But now there are new bounds because there's really a second expansion going on in powers of t. And these new bounds relate the t-dependent coefficients to the t-independent coefficients. Really, you should think of these as being the first two in some infinite tower of constraints on these EFT coefficients. And the list of known constraints is basically growing every month. But they really all stem from these same fundamental properties of locality and causality, namely this dispersion relation, and unitarity, namely this optical theorem. So for the remainder of the talk today, I'm really going to focus on these two simplest positivity bounds and show you how they can be used to impact field theories in cosmology. So these bounds have the potential to greatly constrain our cosmological field theories. But there's an issue. The scattering amplitudes that I've been describing so far, they're really only defined around a Lorentz invariant vacuum. But in cosmology, we're often interested in vacua or background solutions in which the fields acquire a time dependence so that the background metric expands in time. So the first strategy I want to describe today to overcome this disconnect applies to covariant theories in which these two vacua are connected. This allows us to compute amplitudes and positivity bounds around the Lorentz invariant vacuum and then import them to constraints on cosmological observables. So let me illustrate this with an example. So here's an action for a metric G and the light scalar field phi, which has an approximate shift symmetry, so it always appears covered by at least one derivative. Now, an action of this form captures many popular candidate dark energy theories, including P of X models and the quartic Horndeski scalar tensor theories. And its cosmological backgrounds are well studied. For instance, there are solutions for phi and the background metric, which mimic lambda CDM, with linear perturbations on top that are characterized by a small number of alpha parameters. And today I'm going to focus on just two of these parameters, namely alpha t, which controls the speed of tensor fluctuations, the speed of gravitational waves, and alpha b, which is called the braiding, the mixing between the scalar and the tensor, or if you like, it's the rate at which dark energy clusters together on large scales. Now, there's a subset of these theories which also has a stable flat solution where phi is 0 and the background metric is Minkowski. And about that solution, I can scatter phi fluctuations and compute scattering amplitudes. There's two different two-particle processes I could consider. For instance, I could have the scalar field phi scattering against any matter field, couples minimally to the metric. And the s squared coefficient of that amplitude gives me the bound G4 prime has to be positive. The other process I could consider is just scalar field scattering against itself. And there are bounds on G2 coming from the s squared coefficient. But more interestingly, there's bounds on G4 coming from the s squared t coefficient. So comparing these bounds with the definitions of alpha t and alpha b on the cosmological background, we see that importing these positivity constraints from the flat solution would require that alpha t is positive and alpha b is bounded from above by 2 alpha t divided by 1 plus alpha t. So now we can see explicitly how these positivity arguments interface with current cosmological data. So here I'm showing you the 1 and 2 sigma contours from current CMB, BAO, redshift space distortion, and matter power spectrum measurements. And these dashed crosshairs are to show you where GR sits, the point 0, 0. Now I should say that these alpha parameters are functions of time. And so to make this plot, we've adopted a parameterization in which the ratio alpha divided by omega dark energy is approximately constant. So these two positivity bounds I can now use to shade this plot in. There's a region which is compatible with unitary causal local UV completion, and then the white region is not. Now what that means is, in future, as these constraints, experimental constraints get even tighter, and we have a better estimate of alpha b and alpha t in the IR, we can use these bounds to learn something non-trivial about the underlying UV completion. Also, we can implement these bounds as an additional theoretical prior when we're analyzing current data. Rather than trying to fit our data using any potentially unphysical values of alpha b and alpha t, we can instead focus on the region of parameter space which we know could have come from a unitary causal local UV completion. So we see that these positivity priors already let us improve the parameter estimation from our low energy measurements. Now, it's not uncommon to see theoretical consistency conditions used as priors in this business. A common one is to have no ghost or gradient instabilities. But what distinguishes these bounds is that their constraining power is coming from the underlying UV physics. If I gave you an EFT, which had a value of alpha b and alpha t in the white region, the EFT could be perfectly consistent. You wouldn't see anything wrong with it. These bounds are really telling you that there's no way to embed this theory in a UV complete model, which is unitary and causal and local. And what that means is these bounds can give us access to qualitatively new insights that would have been perhaps counterintuitive from the point of view of the EFT alone. For example, this bound on alpha t, that it's positive, corresponds to gravitational waves on this background traveling faster than any matter field, including light. You might have thought that superluminal gravitational waves would be signaling a violation of causality, but these bounds are showing that, at least in these simple theories, that's not the case. That actually UV causality is telling you that gravitational waves have to be traveling faster than any matter field in the theory. The other point to make about the speed of gravitational waves is that following LIGO's multi-messenger detection, we know that at LIGO frequencies, the speed of gravitational waves is very close to that of light. And I haven't added that on this plot here because really I'm focusing on large-scale cosmological observations, and LIGO frequencies can be very close to the cutoff of these dark energy EFTs. So finally, let me stress that this strategy of using a covariant theory to connect these two different vacua, it really only applies to a subset of these theories. In particular, ones which have these two different solutions, they're both stable, and for which the bounds that we evaluate on the flat background, these G4s evaluated at phi equals 0, can be extended, can be applied as cosmological bounds about the background where phi depends on time. So for this special subset of scalar tensor theories which satisfy these requirements, we can do this importing, and these are the results. And it's really providing an important proof of principle showing how these positivity bounds can impact our data analysis and improve our parameter estimation of these EFT coefficients. So the second strategy I want to tell you about today does away with this covariant theory and the need for a separate Lorentz invariant VEV. Instead, we can consider scattering scalar fluctuations directly on the cosmological background. But this requires revisiting the fundamental ingredients that underpin the positivity bounds, since now this background spontaneously breaks Lorentz invariance. And until earlier this year, it really wasn't known how best to proceed in situations where you don't have the full Poincare group. So what I want to do now is sketch very loosely in each of these boxes how we adapted these ingredients for situations in which boosts are broken by the background. Firstly, what we do is focus on scattering fluctuations whose energies are much bigger than any background scale, but still low enough that gravity is weakly coupled. Because for these fluctuations, the background seems static. They don't feel the changing in time. It's like scattering in some sub-horizon box. On time and length scales that are sufficiently small, you can define an S matrix. Now, the resulting sub-horizon amplitude is invariant under an approximate time translation symmetry. And the three boosts that are broken means that the amplitude now depends on three additional variables, which we can take to be the energies of particles 1, 2, and 3. Say the energy of the fourth particle would then be fixed by energy conservation. So already this shows that something has to change compared to the Lorentz invariant story, because before we showed that taking two partial S derivatives of the amplitude at fixed t resulted in a positivity bound, and that can't be applied naively here because we need some prescription for how to hold these additional three energies fixed when taking the partial derivatives. So it turns out that this complication really impacts causality and the dispersion relation, but that actually unitarity is almost unchanged. You can use unitarity to show that the imaginary part of the UV amplitude is still bounded, still positive. The only difference is that now in the forward limit, you're not just setting t equal to 0, but also the energies of particles 1 and 3 have to be the same. So the way we were able to prove this is by taking the Lorentz invariant proof, which uses boosts to go to the center of mass frame and expands the amplitude in terms of partial waves. And we adapted this expansion for a general center of mass motion, showing that the imaginary part of the amplitude remains positive even when you break boosts and you can no longer freely go to the center of mass frame. To relate this UV bound to the EFT coefficients, we make use of the following dispersion relation. The key is that now these S derivatives and this S integral are performed not just at fixed t, but with the energies of 1 and 3 fixed, and also this special ratio S minus U divided by omega 2 fixed. Now, why this ratio? Well, again, it's related to how the dispersion relation is proven in the Lorentz invariant case, where typically boosts are used to go to the so-called bright frame in which the momenta P1 plus P3 vanishes. And as a result, the energies of the particles in this frame are simple analytic functions of S. So we adapted these arguments for a general set of energies. Mathematically, this amounts to finding a change of variables which replaces all of the energies with analytic functions of S and these constant parameters gamma and m. But physically, what this is telling you is that you should take these S derivatives holding the total momentum P1 plus P3 of your subhorizon box fixed. So really you're varying S, the interaction energy inside the box, without varying the speed at which your box is moving through spacetime. So using these variables, we were able to prove this dispersion relation to any order in perturbation theory. And we argue that it should also hold non-perturbatively, providing that this AUV can be represented in the UV theory in the unbroken phase as a correlator of Froissart-bounded local operators. So putting these ingredients together, we arrive at a positivity bound, which looks very similar to the Lorentz invariant bound, but really the key is that now these S derivatives are performed with a particular prescription of how to hold the energies fixed. And you should view this as the first constraint in some tower of constraints which bound every higher order EFT coefficient. So these results that we've achieved on the technical side mean that we can now consider applying positivity bounds directly to scattering on a cosmological background. And so we can constrain a much wider class of cosmological field theories, including those that may not have stable Minkowski solutions. So what do these positivity bounds mean for inflation? Well, adopting the second strategy, we can consider the EFT for scalar fluctuations produced on an inflating spacetime background. Up to fourth order in the scalar pi and at leading order in derivatives, there are 6 interactions shown here, which really can be thought of as determining the power spectrum, how correlated are pairs of points in the CMB, determining the bispectrum and the trispectrum. Of these 6 EFT coefficients, the alphas and the betas, only 3 are independent, which we take to be beta 1, which controls the trispectrum, alpha 1, which controls the bispectrum, and CS, the sound speed of the scalar pi. Now, computing the amplitude from this action for 2 pi's to scatter into 2 pi's, and taking 2s derivatives, we find that this positivity bound becomes a lower bound on beta 1. Namely, the trispectrum has a minimum value set by the bispectrum. No matter how ingenious our UV model building, if the UV physics is unitary, causal, and local, a large bispectrum in the IR necessarily comes with a large trispectrum. Now, observationally, we have much better constraints on scalar cubic non-Gaussianity than we do on beta 1 on the trispectrum. And so what this bound lets you do is use the measurements that we have of alpha 1 and CS to constrain beta 1, really to bootstrap information about the higher point non-Gaussianity from observational constraints on lower point non-Gaussianity. And in fact, it gets even better because we can place an even stronger positivity bound on this EFT that removes beta 1 altogether and just constrains the shape of the bispectrum. To do this, we go back to the dispersion relation, which schematically relates the EFT amplitude to an integral over all energies of the imaginary part of A. But what we can do is split this integral up into 2 pieces, a low energy part where we integrate up to the scale of new physics, omega np, at which the EFT breaks down, and a high energy part where we integrate from omega np up to infinity, beyond the EFT. Now, we might not know this UV part explicitly, but unitarity guarantees that it's positive. So we can write a stronger positivity bound, which requires not just that this EFT amplitude is positive, but that it's greater than some integral that we can compute within the EFT. Doing that for this action here, we find that there is a bound on the scale of new physics, on the cutoff of the EFT, entirely from alpha 1 and CS, the coefficients that determine the power and bispectra. So unitarity, causality, and locality are really telling us when this EFT has to break down and physics beyond single field weakly coupled inflation has to become important. Now we can compare this with the Planck 2018 constraints from the equilateral and orthogonal shapes of non-Gaussianity in the CMB. So this purple region corresponds to the values of alpha 1 and CS for which new physics must appear below 60H, which is approximately this scale here, m Planck h dot. In this blue region, new physics has to appear below 20H. And in this red region, this EFT really has to break down at some point below 10H. Now, the majority of this 1 sigma confidence interval, positivity implies that new physics beyond this single field EFT enters below 10H, within an order of magnitude of the horizon. So as future missions come online, searching for signs of new physics using primordial non-Gaussianity, it's really vital that we continue to improve these theoretical constraints so that we can maximize our discovery potential. So now we've seen how positivity constraints on EFT coefficients arise from unitarity, causality, and locality in the UV. And we've seen 2 examples of how they can be applied in cosmology to both dark energy and inflation. So to wrap up this talk, I want to highlight the next steps in this positivity program. Our focus thus far has really been on sub-horizon scattering. And this is largely for 2 reasons. First, these objects are easy to compute, at least on sub-horizon scales, and they bear enough similarity with the amplitudes of particle physics that it is often very clear how to manipulate them. For instance, the ingredients that went into the positivity bounds, unitarity and causality, they ultimately constrain the sub-horizon object in much the same way as in particle physics. Unitarity gives us an optical theorem, which at the level of Feynman diagrams is a simple set of cutting rules. And causality gives us a dispersion relation, or more generally, it guarantees analyticity in the complex S-plane. However, the inherent limitation in this approach is that we are restricting ourselves to sub-horizon scales. We cannot apply this technology when any energy approaches the Hubble scale, since then time translations are no longer an approximate symmetry. Energy is no longer conserved, and in fact, near the horizon, the very definition of an S-matrix element can break down. So in order to push positivity to the horizon, we need to formulate these bounds in terms of a different observable. So one candidate which has attracted a lot of attention recently are the so-called wave function coefficients. These are essentially the Taylor series coefficients of the wave function of the universe at time t. These coefficients are often more difficult to compute, but they are defined on a whole time slice of the expanding Poincare patch, and so they capture all of the horizon scale physics. And what's more, when this t is taken to be the boundary of the expanding spacetime, these objects are the natural target of holography. Now, very recently, we were able to show that unitary time evolution in the bulk spacetime actually implies a set of cutting rules which we developed to any order in perturbation theory, and we're able to use them to compute for the first time the one loop correction to the power spectrum in the EFT of inflation. However, it is not yet known how causality is encoded in these objects. We have no dispersion relation to connect the UV and the IR. And this is really one of the key missing pieces to establishing positivity bounds directly on the wave function. So from my perspective, the next big breakthrough for cosmological positivity bounds will be developing our understanding of these wave function coefficients so that one day we will be able to move beyond the subhorizon amplitude, constrain the wave function directly. In the meantime, though, this subhorizon technology is what's currently available. And as we have already seen, it is now mature enough to place non-trivial constraints on our cosmological EFTs. And so we should now also be exploring the impact that these bounds have on other models of inflation or dark energy. To sum up, positivity bounds are a set of powerful UV-IR relations which use basic UV assumptions such as unitarity, causality, and locality to establish constraints on the EFT coefficients appearing in any scattering amplitude. In order to apply this machinery to cosmology, the main hurdle to overcome is that the expanding background spontaneously breaks Lorentz invariance. Now, one strategy is to focus on covariant theories in which there is a Lorentz invariant vacuum near to the cosmological one so that we can import flat space positivity bounds. And for a subset of quartic Horndeski theories, which have such a stable vacuum, then these bounds can greatly improve our estimation of the low energy parameters of this EFT, particularly when paired with current data. But a second strategy, which removes the need for this separate flat vacuum, is to consider scattering scalar fluctuations directly on the cosmological background. On subhorizon scales, time translations can remain an approximate symmetry, and so only boosts are broken by the background. In which case, this amplitude is now a function of 3 additional variables. But assuming the analogous small-scale properties, namely a dispersion relation, which smoothly connects this low-energy amplitude to some correlator in the UV, which is bounded by the optical theorem, we have been able to derive an analogous set of positivity bounds. And applying them to the EFT of inflation, we find that these UV properties impose a minimum threshold for the parameter which controls the trispectrum, and also can be used to infer the scale at which the EFT breaks down, and new physics beyond single field weakly coupled inflation must become important. There are now a number of ways forward as we extend this positivity program in the future. Now, one important route is to take these newly developed tools and apply them to a wider variety of different models. For instance, going beyond the simple Horndeski scalar-tensor theories, possibly including dark vector fields or other light degrees of freedom, or even extending the leading order EFT of inflation with the higher derivative terms characteristic of the EFT of dark energy. The other important route forward, though, is to further develop these tools, improving these positivity constraints and extending their regime of applicability. In particular, there have been many advances in the last year or so in the Lorentz invariant literature, exploiting moment theorems and full crossing symmetry to derive stronger two-sided positivity bounds. And it seems likely that much of that progress can be imported also to subhorizon scattering amplitudes in cosmology. Finally, if we are to go beyond this subhorizon limit, we must eventually move away from these amplitudes and consider another observable, such as a wave function coefficient. And we have recently uncovered how these wave function coefficients are constrained by unitarity. And so the next step is to go after causality and find a dispersion relation which connects the UV and the IR. Altogether, alongside an increasing pool of cosmological data from current and future missions, There are also new theoretical tools becoming available, and these have the potential to greatly improve the constraining power of our data and guide us in the search for new fundamental physics. Thank you.